Welcome to a course on the design and analysis of algorithms. This screencast is an overview of the content of this course. The goals are to develop your skill in developing algorithmic solutions to problems and proving that those solutions work and understanding their performance. This will involve using multiple design approaches, mastering some important algorithms that are classic in the field, and developing your problem-solving skills along the way. In addition, you develop a deeper understanding of asymptotic complexity and proving that algorithms are correct. Finally, we will study some approaches to dealing with difficult problems for which we currently have no known polynomial time algorithms. This course assumes a course in discrete math for computer science, including a familiarity with graphs, counting, basic proof techniques, and big O notation. Why would you study algorithms? Well, by studying algorithms, it helps you to become better at design and development. So knowing the essential basic algorithms that have proven effective in the past helps you design and develop for the future. Also, algorithms have a huge impact on society. Just think of the internet or Google search. They involve problem-solving skills, which many people enjoy. Hopefully you're one of them. And finally, it can be fun to solve problems. And that's what this course is about. As I mentioned on the last slide, we're going to cover sort of the greatest hits of basic algorithms. And in doing this, you're going to develop your vocabulary for the design and analysis of algorithms so you can communicate with other professionals. We're going to look at algorithms that have designs that carry over to more complex algorithms that you might run into in the future, solving more complex problems than you've seen here in this course. They'll involve graphs, divide and conquer algorithms, greedy algorithms, dynamic programming algorithms, iterative improvement algorithms, and finally, at the end of this course, we're going to talk about dealing with the complexity and the limitations of our current understanding of what algorithms can be solved in an efficient fashion. This course is designed around the idea of a flipped classroom. What that means is that we'll no longer be doing a traditional lecture lab format. All the time we spend in class together will basically be similar to what we would normally do in labs, plus little mini quizzes and working through examples and potentially beginning some of the more difficult assignments. So before class, you're expected to watch the relevant videos, read any notes that are provided, and potentially you should access one of the textbooks for more details on the material that you're assigned. During lecture and lab, though, as I said, there'll be individual and group quizzes. You'll work through examples to illustrate problems and algorithms, find counterexamples to show algorithms are not correct, and designing algorithms, proofs of correctness, and analyzing algorithms. So you'll be doing in both lecture and lab the kinds of things that reinforce your learning, and you'll have an opportunity. One of the big advantages of doing it this way is you'll have opportunity to get feedback as you're doing it, because myself and potentially some TAs will be in the lecture and in the lab. One of the advantages of the screencasts, watching the videos, is of course that you can pause the material and go back and rewatch sections for which you're having difficulty. One of the things that I strongly encourage you to do as part of watching the videos is take notes and write down any questions that you might have so that I can answer them at the beginning of class. Finally, because of this, attendance at lecture and lab is mandatory. You'll be writing many of your algorithms in pseudocode. Many of the algorithms that I present in the screencast will be presented in pseudocode. And so basically, if you haven't done it recently, I just want to remind you, the idea is to specify the algorithm in detail, but without any worry about the underlying syntax. So it should be rigorous, but without the overhead of a programming language syntax. So all the normal things that you find in a standard programming language, if then else, for loops, while loops, switch statements or case statements, function calls, the usual data structures, including arrays and sometimes lists, and all the usual data types. Finally, you're expected to comment your pseudocode and use whitespace to show flow of control. Most of you have had Python, so you use whitespace similar to the way you do in Python to show how the flow of control is going to go in the program. This slide generally shows the overall process for developing algorithms, and it's one that we're going to follow a lot in the problem solving and the algorithm development that we're going to do in this course. Namely, you start out with some problem, and in the real world you might have to spend a fair amount of time refining the problem and making sure that you understand what the client's problem actually is. For us, most of the time that'll be pretty straightforward. But then you have to brainstorm possible solutions. You have the different design approaches to help you do that. Once you come up with some kind of proposed solution, then you move on to deciding whether your proposed solution is going to be correct. You look for counterexamples, and then if you can't find any counterexamples and you become pretty convinced of its correctness, then you try to prove that it's correct. Once you're done with that, then you get into the analysis stage. So one of the important things that things to watch out for that many students do is they start worrying about efficiency before correctness. It's much more important once you have a correct algorithm, even if it turns out to be pretty inefficient, it leads you, the understanding of a correct algorithm can lead you to a more efficient algorithm. Whereas if you've got an incorrect algorithm, that's really unlikely to, even though you've analyzed it and it's going to be fast, that's not likely to lead you to a correct solution. As you can also see on this slide, there's no straight line from brainstorming through correctness to analysis. Many times you'll have to go back and re-brainstorm, come up with a new algorithm, or once you do the analysis of its performance, you might say, well, it's too slow, and you have to go back again and do the brainstorming and correctness and analysis once again. A little disclaimer here, there's not enough time in this course, it's only a quarter long, to do everything. We're going to focus on really sort of two things, correctness, and that might include determining that an algorithm actually gives you the best answer, and then time efficiency. And for the time efficiency, we're mostly going to be doing theoretical analysis. So there's going to be a lot left out here. Two of the main things are space. We're not going to spend much time worrying about space, nor are we going to do much with empirical analysis. There'll be a couple of labs and assignments that try to get at some of the tools there, but what we're going to have to do is just focus our efforts on the theoretical analysis and correctness. Now, this is not these other things that we're not going to study are still very important, but they take a fair amount of time. In fact, you could easily spend a whole quarter or even a whole year on how to do empirical analysis well. To get the course off on a concrete foot, we're going to talk about exhaustive search. Lots of problems can be thought of as search problems. A search problem is a problem that involves some set of possibilities, and we are looking for one or more of the possibilities that satisfy some property. So some examples that we'll talk about in detail during the course are searching, say, for shortest path from one city to another, or searching for the best combination of items to make in a factory. For some of these problems, we're going to need to understand and perhaps generate a set of all the possibilities over which we will search. And that's where we're going to start. And how does exhaustive search work typically? Well, we generate a list of all the possible solutions to the problem and evaluate those potential solutions one by one, disqualifying infeasible ones, in other words, ones that don't meet some conditions that must be satisfied. And for optimization problems, we keep track of the best one that we've found so far. What this will involve initially, and the next screencast we'll talk about in the context of a couple of concrete problems, is developing all the permutations of some set of things or all the subsets of some set of things. So typical counting problems that you should have seen in discrete mathematics, we're going to take to the next level and see how they really apply in many concrete situations in computing.